Hello everyone, this is Musimenta Tendo Divine, a student in Makerere University offering software engineering. And today we are going to dive into the intriguing realm of artificial intelligence in this presentation with examination of a very practical application that is yet to be built, the campus crowd detection and recommender system. This system is to be created. This system was created to help manage crowd densities on campus and ease students' movement around campus, reducing waiting times. And the quest for artificial intelligence (AI) has involved dreams of creating machines with human abilities, and this presentation explores the foundations through the lens of our application. Yes, and this content came from ALISON schools, where I took a diploma course in fundamentals of artificial intelligence plus some knowledge from our AI project that is yet to be built. Now let's talk about the historical background of AI. But before talking about the new technologies, let's talk about the history. So to start with, I want to define the term artificial intelligence, which is the ability of a machine to seemingly think and perform tasks that require human abilities, such as learning, reasoning, and problem solving. Now, to go into the historical roots, dreams emerged about machines with human abilities, automators that move, and devices that reason. Human-like automators are described in many stories, pictures, paintings, drawings, and sculptures. To begin with, I would like to begin with this first robot, which was created in 1900 by Frank Baum, who created the tiny woodman, who featured in the literature of Wonderful Wizard of Oz, as you can see there on the screen. Then Leonardo da Vinci in 1495 designed a humanoid robot as a knight, as you can see there in the picture. Then Karel Capek introduced the term robot in his play RUR, which means Ransom's Universal Robot. As you can see, this is how the robot looked like on your screen. Then Dr. W. Greywater in 1948 built Elmer and Elsie, robots without pre-programming that could recharge their own batteries. That's how they looked like. And then Thomas Hobbes in 1651 hinted on building artificial animals, earning him a title of the patriarch of artificial intelligence. Then Jacques de Vaucanson's mechanical duck in 1738 and John Mary's automated law that worked on patch cards. As you can see, the duck is there, and then the law is here. Then Alan Turing came in in 1950 and laid the groundwork of modern intelligence with his landmark paper, Computing Machinery and Intelligence. He began this paper by posing a fundamental question: can machines think? This debate and this question immediately highlighted a debate around computer intelligence and how to really define thinking. Turing also introduced the famous Turing test or imitation game in his paper proposing a behavioral criterion for machine intelligence based on a computer's ability to give responses distinguishable from humans. Finally, the field of AI as we know it today was formally established in 1956, and the term artificial intelligence was birthed during a 2-month 10-main study conducted in the summer of 1956 at Dartmouth College. This study built a premise that any aspect of learning or intelligence could, in principle, The precise this term artificial intelligence was coined by John McCarthy, who was in this meeting, and then it started and they named him as the founding father of artificial intelligence. Then let's go to the next, where that's Alan Turing. I had not shown you the pic. I have a graphic of the history of artificial intelligence. I would like us to dive through the dimensions of and multidisciplinary foundations of AI. As we said, artificial intelligence is the ability of machines to seemingly think and perform tasks that require human knowledge, such as learning, reasoning, and problem solving. It is also a field dedicated to building artifacts that display intelligent behavior. So it's not a single concept. It is approached and defined in various ways, as the research says that it has 4 dimensions, such as and these are thinking humanly, thinking rationally, acting humanly, and acting rationally. Thinking humanly is basically modeling human cognition, the ability of a human, basically modeling human cognition, which is the ability of a human to think and reason. So we model that in terms of artificial intelligence. Then thinking rationally is basically formalizing the inferences, and then acting humanly is exhibiting human behavior, being able to act like a human. Then acting rationally is being able to do the right thing as a human being would do. And this brings us to an example of Aristotle, who was the first to codify thinking in, as you can see there in the pic, that's how he looked like by then. I don't know if he still exists. And his syllogisms provided patterns of argument structures that always yielded correct premises. So he said if all computers use energy and using energy generates heat, then all computers generate heat. This ancient philosophical groundwork laid a crucial basis for logical reasoning in machines. However, there are obstacles to this purely logical approach, and not all intelligent behavior is mediated by logical deliberation, and formal knowledge can be difficult to model due to its uncertainty. Then, after that, we look at the core components of AI systems. The core components of AI systems are interactions with the real world, perception, understanding, and actions, like how the systems perceive data, understand it, and act accordingly to that data. Now, in our system, how the system is able to get that data about the geolocation data of different areas, how it understands it, and how it is able to act upon it by giving recommendations and knowing that this is data, this is a less crowded area and this is a more crowded area. Then it's also important to recognize that AI is not solely a subfield of computer science. It draws its knowledge from multiple disciplinary endeavors such as philosophy, mathematics, and philosophy contributes logic, methods of reasoning, and discussions on mind as a physical system. Then mathematics provides formal representation, proof theory, algorithms, and concepts like decidability and tractability. Statistics and probability are essential for modeling uncertainty and learning from data. Then economics informs utility and decision theories. Then neuroscience helps us to understand neurons as information processing units. Physiology and cognitive science explores how people behave, perceive, and process cognitive information. Computer engineering focuses on building fast computers, and control theory deals with designing systems that maximize an objective function over time. Even linguistics contributes to knowledge representation and grammar. This coverage of different disciplines highlights the complexity and richness of AI research. As we think about the different ways AI can be conceptualized as something that thinks like us, acts like us, and thinks purely, logically, or acts rationally, I would like to ask you, which dimension of AI do you find more compelling or perhaps more concerning? As we go to the next slide, you can answer that question in the comment section below. Trace the historical development of artificial intelligence and see how this journey leads us to a kind of AI like the campus crowd detection and recommender system. The history of artificial intelligence has been marked by cycles of great enthusiasm followed by periods of realism. Early beginnings in 1943 saw the Boolean circuit model of the brain. The 1950s brought initial promises with Alan Turing's seminal paper that the first machine learning program and the logical theorist. This led to periods of great enthusiasm between 1955 and 1965, as you can see there in the picture, highlighted by Dartmouth meeting where the term artificial intelligence was officially adopted in 1956. Projects like the General Problem Solver and invention of leap language emerged from this era. However, in 1966 to 1973, reality dawned. Researchers realized that many AI problems were intractable and limitations of existing neural network methods were identified. The period of 1969 to 1985 focused on adding domain knowledge through the rule-based expert systems like Dendra and Mycin. By those systems often proved brittle and did not scale well in practice. Yes, we are talking about all these milestones. Then a critical turning point in 1986 onwards, with the rise of machine learning. This period saw the return to popularity of neural networks and major advances in machine learning algorithms and applications. This further propelled the beginning 1990 role of uncertainty with a development of bias networks and new knowledge representation frameworks. By the beginning of 1995, AI was emerging as science, integrating learning, reasoning, and various AI methods used in fields like data mining, computer vision, and natural language processing. This shift represents a significant evolution in data processing. We moved from early symbolic or purely rule-based system to sophisticated statistical and deep learning approaches, which are fundamentally data-driven. And the timeline shows machine learning encompassing supervised learning and reinforcement learning with deep learning primary focus driving the development of narrow AI. So where does campus crowd detection and recommender system fit in this history? The campus crowd and detection and recommender system is a primary example of a modern data-driven system narrow AI designed for practical problem solving. it leverages or uses spatial intelligence algorithms and uses real-time geolocation data collected from students' devices to estimate crowds and be able to recommend and solve the problem of overcrowding around certain service points in campus. So this brings us to our introduction to our AI system, the campus crowd detection and recommender system, which are going to relate to some concepts that I studied from ALISON. Our problem statement in this system is university campuses face persisting challenges with crowd densities around busy service points like cafeterias, dining halls, and libraries. And the system is here to solve this problem, and it estimates real-time crowd sizes around different points using their geolocations and recommends the more less crowded areas in the nearest location. And our overall goal is to ease campus movement and reduce students' waiting times in different places like dining halls, cafeterias, and also improve the overall campus experience. This system's functionality, it mimics human cognitive processes to evaluate the different options around campus. And it is built to directly tackle the everyday frustrations. And to proceed, now we are going to dive into how the campus crowd detection and recommender system operates, like its technical foundations and how it works. At its core, the system relies on a critical piece of information, like the geolocation data for students from their mobile devices when they turn on their locations. Then it employs spatial intelligence algorithms to analyze the data and determine the crowd densities. And the outcome, it generates an actionable recommendation for less crowded areas. Maybe you want to go to a less crowded cafeteria. It can process your location and also other people's location and see the clusters in different locations, and depending on the algorithm, the size of the cluster, the smallest size of that location cluster is where it will recommend you to go, and then you decide to go there or you don't. Then yes, and the underlying assumption is that every student must have their phones charged with their locations enabled to enable the detection of the different areas in campus that are crowded or less crowded. Yes, and the system uses geolocation and spatial intelligence for navigation, which relates to the Howard Gardner's spatial intelligence. Yes, and to proceed, we shall go to the next slide and talk about. So moving deeper in the system's mechanics, let's explore the data sources it utilizes and how it processes the information. As we discussed, the primary data source of this system is geolocation data collected from students' mobile devices. This allows the system to accurately estimate crowd sizes in real time by understanding where active devices are located on campus. However, to enhance accuracy and robustness, the campus crowd detection and recommender system design is the capability to engage multiple data sources that, while our current iteration heavily relies on device geolocations, feature enhancements like use of CCTV camera footage or computer vision, or even incorporating academic schedules. For example, students' devices are often in all location services disabled. We could use computer vision CCTV cameras to detect those crowds. though it would require explicit programming, but yes, we shall look into that. Now let's look at how data is processed. There are two main types of data analysis here at play. We have the real-time data analysis, which involves immediate assessment of current crowd levels. The system continuously processes the incoming data about geolocations from devices that are detected in different places with large crowds at that particular point, enabling us to get instant recommendations. Secondly, we shall use historical data. By looking at past data, the system can learn patterns such as peak hours of certain location or days when the libraries are typically busiest. While the current system primarily follows pre-programmed rules, integrating diverse data sources like academic timetables is in the future, and we are thinking about it. So this allows the system to be more accurate and give more accurate recommendations depending on the given areas you've put that you need that data for. Now let's move on how the system accurately delivers its core functionality as it interacts with users. The engine of this system it uses spatial intelligence. It uses spatial intelligence to detect real-time data and analyze different crowd densities, and it gives you recommendations. And this structured approach to this problem solving aligns with logical mathematical intelligence, but the challenge for the system to consider broader context introduces the frame problem, which we shall talk about in the upcoming slides. And now let's go to the next slide, which talks about. Let's look at the campus crowd detection and recommender system as an AI problem solving example. And here we are going to formally frame up the problem so that the system can be able to solve it. And this is often done using what's called the state space search. And this state space search, I got to learn about it from the diploma course I took from ALISON schools, which is called the Fundamentals of Artificial Intelligence. And I realized that in AI, problem-solving tasks are formulated as such in state space. And this involves defining the three key components. You define the initial state, operators or actions, and then the goal state. And in our system, we can apply this framework. So we take the initial state as the current crowd distribution around the campus service point, and then the operators or actions to be the students' movement and interaction with these locations, and then the goal state or objective, the successful access to less crowded service points by the students, which optimizes crowd flow and reduces the waiting. And this formal structuring of the problem, defining the state, the actions, and the clear objective is crucial for any artificial intelligence system because it uses logical reasoning and problem organization, allowing computers to process information systematically towards the solution. And this approach of skills is associated with the Howard Gardner's logical mathematical intelligence, which is about understanding logical patterns and efficiently and effectively solving problems. And to proceed, we are going to go to our next slide. Now, having understood how to formalize a problem, let's look at problem solving using the search strategies. And search in AI involves finding a path from an initial state to the goal state within a search space. And there are two categories of search strategies. We have the uninformed search strategy, which is called the blind search, and the informed search strategy. The uninformed search strategy is where no information about the problem domain is used. And some of the examples, such as the breadth first search, which expands the shallow unexpanded node first, guaranteed to find the shallowest goal. And then we have the depth first search, which expands the deepest unexpanded node first. And then we have the uniform cost search, which expands the node with the smallest path cost. Now let's move to the next search strategy, which is the informed search strategy that uses problem-specific knowledge to guide the search. This problem-specific knowledge is known as heuristics. And this type of search is far more efficient because of its heuristic nature. And a heuristic function estimates how close the state is from the goal, which helps the system to be more intelligent and make more intelligent choices when it is making a search. Heuristics significantly speed up the search process compared to the other strategy known as the uninformed search strategy. But you may be there asking yourself, how does this apply to the campus crowd detection and recommender system? The system's core purpose is to detect crowds and recommend less crowded alternative service points. So it needs to search for the optimal path or alternative location for students given the current crowd situation. For instance, if the main library is crowded, the system searches its knowledge base of alternative study points that are currently less crowded. Effectively solves the real-time navigation problem. Yes, as we move to our next slide, and let's talk about knowledge representation and reasoning in the campus crowd and detection and recommender system. The system encodes knowledge and rules using symbolic representations such as first-order logic. And this knowledge can be broadly categorized in three types. First is the declarative knowledge, which is knowledge about a problem and it includes specific facts. Then secondly is the procedural knowledge, which defines how to solve a problem and often represented in rules or general information that allows the manipulation of declarative knowledge. So the third one is the control knowledge, which involves processing strategies and structures used to coordinate the entire problem-solving process. Now let's look at our system. The system processes geolocation data and it operates under defined rules. For example, if the number of phones in cafeteria A, let's say, is greater than 150, then we can tell it to label that cafeteria as crowded and be able to recommend any other service point. So if this demonstrates how the system processes input and generates actionable recommendations. It's programmed to strictly follow these rules and logic without deviating from its instructions. Like expressing operational rules connects to linguistic intelligence, association rules can be transformed into first-order logic expressions like the example I've given, then the system's reasoning by following these rules can touch on interpersonal intelligence if it could adapt or refine its own rules. Yes, and now we are going to move to the next slide, which is the inference in first order logic, deduction and understanding. How AI stores and systems draw conclusions from the received information. This process is called logical inference. Inference is deriving facts or conclusions from the existing knowledge, often using deductions, and the key concepts are soundness, completeness. Soundness ensures that the inferred conclusions are true if premises are true, and then completeness ensures that all true conclusions are inferred. And this application, the classification outputs can act as facts. Inference rules derive new labels. For example, in our campus crowd detection and recommender system, if the student wants to read and there is a less crowded library B, imply B. The inference rule helps the system to derive recommendations. This relates to logical mathematical intelligence for deriving truths, and the philosophical debate context in this way is inferred. So in a philosophical debate context is inference. So this brings us to the philosophical debate context. Is inference real understanding or merely symbolic shuffling? And this question is central to the Turing test versus the Chinese room argument debate. Let's proceed and see. So we are going to see and address a critical real-world challenge in AI, uncertainty, and how systems are designed to handle each. Reasoning under uncertainty for robustness. AI systems often deal with incomplete, noisy, and uncertain data. How should our system respond to such data in case it is a need? If the geolocation data is sporadic, unreliable, or missing for some users, the Bayesian reasoning and other probabilistic models enable artificial intelligence systems to make informed decisions even with imperfect information. This relates to probabilistic classification methods such as the naive Bayesian network in data mining, handling incomplete natural signals, connects to the naturalistic intelligence. Now let's talk about planning and decision making for intelligent systems. Planning is defining a sequence of goal-directed actions to achieve specific outcomes. And decision making extends planning by linking it with utility or value of an outcome and risk assessment. An advanced campus crowd detection and recommender system could move from a simple recommendation system to a complex planning, e.g., dynamic routes based on the predicted crowds or detected crowds that are in the different areas or service points, and advising the campus management on resource allocation, like where to put more canteens, where to put more cafeterias, how to coordinate different crowds. And the sequencing actions relate to body kinesthetic intelligence. Balancing social and personal goals in decision making touches upon interpersonal and intrapersonal intelligence. Now let's go into our next discussion, which is going to machine learning fundamentals. Machine learning as the engine of modern artificial intelligence. First of all, machine learning allows systems to learn from data without explicit programming. And machine learning involves three types of learning. We have supervised learning, unsupervised learning, and reinforcement learning. But today we are going to only talk about two. First of all, supervised learning involves where models learn from labeled data. A model is given data that is labeled, and then the output data is also labeled, so it learns from already labeled data. This involves things like classification, where you categorize data where data is categorized. For example, sign language recognition systems that use gesture data sets, and spam emails, and categorizing spam emails and non-spam emails. Then there is also regression, where there is predicting continuous values like stock market prices, house prices. And then we go to the next type, which is unsupervised learning, where models learn from unlabeled data and find their own patterns in those data. And this involves clustering, where models are able to group similar data points and find similar data. And this applies to our campus crowd detection and recommender system in a way that, since it uses geolocation, when a device is connected to device location is turned on, the number of devices in a particular area indicate the amount of clustering in that particular area, which when we write algorithms for that if a number of geolocation data is people around there whose devices are connected to, whose locations on is more than 150, then take that place to be overcrowded and recommend another alternative with less number of those people. So our system is going to be trained on data that is unlabeled, or we can even label it, but since it will be using clustering, I believe it will be detecting better using that kind of data. And key data mining concepts, pattern recognitions connect to logical mathematical intelligence, and environmental signal analysis connects to naturalistic intelligence. And this brings us to the superhuman intelligence debate, that machine learning will eventually surpass human abilities in all domains. Then let's move forward on weak AI versus strong AI. And here we are going to categorize the campus crowd detection and recommender system. First of all, weak AIs, or weak artificial intelligence systems. These machines can act intelligently without genuine consciousness and understanding, or a mind to understand what they are doing or be aware of whatever they are doing and understand the reasons behind what they are doing. Then strong AIs, these ones are able to understand, or maybe have a mind, or understand and are able to be self-aware and have cognitive states, becoming a person. These ones can be able to understand what they are actually processing or what they're doing, and they can be like humans, but I believe these ones have not yet been achieved, because there has not been any brain that has in artificial intelligence has been developed as a brain of a human being that is able to understand, reason everything behind what they are doing. And our system functions as a weak AI because, of course, strong AIs have not yet been brought into play. So it functions as a weak AI because it follows pre-programmed rules and manipulates symbols like geolocation data without any consciousness or knowing anything behind what they're actually processing. They can't understand what a crowd is or what a service point is, but they have been programmed to actually do something that is close to human thinking, so they don't understand what exactly it is. And this distinction is fundamental to philosophical debates about AI capabilities. Then moving on, we are going to look at the Turing test, a behavior view of intelligence. This Turing test was proposed by Alan Turing in 1950. A human interrogator interacts via text speech with a human and a computer. So if this interrogator cannot distinguish between the computer and the human, then the computer passes. So if the system's recommendations, now this is taking us to connecting this to our system. So if the system's recommendations were indistinguishable from human advice, then this would satisfy the Turing test behavior criteria. So if at that moment the system can do what a human can do, then this satisfies the Turing test behavior. However, passing the test does not imply genuine intelligence or thinking. It could just be following predefined rules. Of course, it will be following predefined rules to give human-like responses. So the Turing test is a cornerstone of debates on machine intelligence. Now let's dive into Turing test. We go to the Seeley's Chinese room argument, which challenges true understanding. John Seeley in 1980 challenged the idea that symbol manipulation constitutes genuine thinking, directly countering the Turing test, and proposed a scenario that a person in a room not knowing Chinese manipulates Chinese symbols using English rules. Like a person is in the room and is given, let's say, a book containing Chinese symbols, and there are different meanings in English. So this person is able to translate this and form rules that have the true meaning in Chinese. To an observer, this appears that a person understands Chinese, but these people are just following syntax, or like the written down symbols and their meaning, without any understanding or comprehension or semantic comprehension behind these symbols. So our system processes geolocation data and produces recommendations by following syntactic rules, but it lacks genuine understanding of the meaning or implication of that data. It does not understand anything about what a crowd is or a service point, as I said earlier, or if a person needs a less crowded area to relax, or like such things. So real human understanding involves semantics, like it involves meaning. Like human understanding, a human understands a meaning behind whatever is happening, which mere form of symbol manipulation lacks, because if a robot can be able to manipulate symbols, but there is more to a brain. A brain is able to understand the meaning behind that symbol. So this raises a critical argument in the debate on AI's understanding versus symbolic shuffling. And moving on, we are moving on to having discussed the Turing test, the Seeley's room argument. We can now move into another significant challenge to the notion of genuine thinking in artificial intelligence. The frame problem, the challenge of context awareness, by Daniel Dennett's. So this was Daniel Dennett's 1969 frame problem, which highlights the difficulty for AI, artificial intelligence, to discern which information is relevant and which factors to consider in the dynamic and changing environment. This limitation of the limitation of the system is that it cannot make contextual judgments. Yes, our system cannot make contextual judgments. For example, recommending a cafeteria that's less crowded, even if a human would know a large crowd is imminent due to an academic schedule or a campus event, unless explicitly programmed. So if our system is not programmed to be able to know the context and be able to judge contextually, then it cannot know the real reason behind the large crowds and others, and the large crowds and the less crowds. Maybe there is a campus event or an exam, something like that. So humans can study situations, filter relevant information, and anticipate changes and understand unspoken social behaviors and cultural complexities. Yes, this means that a human can actually, now like me, I'm in school, I can know that there is an event at campus. I filter, I know that this is an event, it's not for me. Maybe let's say it's like a party, maybe freshers ball, it's not for me, but if the area is crowded, I can know that this event is going to take from maybe like 6 to 12. So I know there will be changes, like the area will be less crowded at 12 a.m. in the night, and know that there is a party, of course, people are enjoying, so it has to be crowded. So without this ability, the system exhibits simulation of intelligence, not actual reasoning and thinking. Yes, this is true. So without this ability to be able to discern what is behind the information, the crowds and stuff, it actually means it cannot reason, it cannot think, it's just following predefined patterns and algorithms. So this is critical for artificial intelligence planning. It concerns selecting relevant preconditions for actions in the dynamic environment. So you have to plan how the artificial intelligence system is going to work, and select those preconditions relevantly for it to fit in the dynamically changing environment. Then moving on to the next slide, which is talking about the future directions, how we will enhance the campus crowd detection and recommender system and super intelligence. So we'll begin with overcoming the limitations. We will integrate diverse data sources to improve the accuracy of detection and adaptability. We're not doing predictive, we're doing detection. So we shall improve the accuracy. We shall increase our data sources. We shall add CCTV camera footage in different areas, if there is areas with CCTV cameras, so that it is able to detect accurately and adapt to that environment very well. So we will also add maybe academic schedules to add maybe like exam timetables. Like this is a season of exams, so we expect the library to be crowded. We expect different reading areas to be crowded, Wi-Fi spots to be crowded, where people are able to access Wi-Fi to be able to access reading materials. Then maybe social media updates, like maybe there is an event or a gathering at campus and it's broadcasted on social media. Then we're able to know that this area, the user is able to know that this area is crowded because there is this event. Then Wi-Fi signals, if the signal is on and off, you'll be able to know that this area is crowded, so that's why the Wi-Fi signals are low. So such integrations would potentially outperform believingly humans in crowd management. And according to superintelligence theory by Nick Bostrom in 2014, intelligence does not have to mimic human thought to be meaningful. Computers may develop a unique form of thinking, yes, but it's still us who develop that thinking. Then ending with a thank you for listening. And in conclusion, I leave with a provoking statement. As artificial intelligence continues its remarkable journey, the mirror still holds up to our own intelligence, and it forces us to continually redefine what thinking is truly. And the quest for thinking machines still continues, reminding us that while artificial intelligence can replicate many aspects of intelligence, the essence of conscious understanding remains a profound mystery. Yes, thank you for listening. This content has been compiled by me, student at Macquarie University, using the ALISON Diploma course in Fundamentals of Artificial Intelligence and our AI project, and besides it is a certificate I received from there. Thank you so much.